Suppose we want to measure the height of a tall pole. We could climb the pole and measure it directly, but that is not always practical. But the pole gives us something easier to measure: its shadow. The pole, the shadow, and the sunlight form a triangle. Now place a smaller object nearby, like a stick. The stick also makes a shadow. The stick, its shadow, and the sunlight also form a triangle. These two triangles have the same shape, meaning they have the same angles. Why? Because both have a right angle with the ground. Since the sun is very far away, the sunlight rays reaching the pole and the stick are practically parallel, so they hit the ground at the same angle. Once two angles match, the third angle must match too, because the three angles in any triangle always add up to 180 degrees. So the pole triangle and the stick triangle have the same angles. Triangles with equal corresponding angles are called similar triangles. Their shapes match, but their sizes may differ. In fact, we will see that one triangle is a scaled version of the other. Their side lengths are proportional. In other words, if the shadow of the pole is thrice the shadow of the stick, then the height of the pole is also thrice the height of the stick. This can be shown using Thales Basic Proportionality Theorem. It says that a line parallel to a side cuts the other two sides in a matching ratio. That is, the ratio of the two pieces on one side, AD over DB, is equal to the ratio of the two pieces on the other side, AE over EC. In our shadow problem, we can construct a congruent copy of the small triangle inside the large triangle with the slanted sides parallel. Its shadow is still S, and its height is still H. The remaining parts are S minus S and H minus H. Now the proportionality theorem applies. Then, with a little algebra, we get the useful result. The shadow ratio and the height ratio are the same. So if we can measure the stick's height, the shadows of the stick, and the pole, then we can determine the height of the pole. A word of caution. It is tempting to say, the sunlight angle is the same, so the slope of the slanted side is the same in both triangles. But the concepts of slope and tangent are built on the very proportionality result we are trying to prove. This inadvertently leads to circular reasoning and is not a valid proof. In fact, Euclid's Elements is famous for organizing the geometry known at the time in a step-by-step way, so that later results depend on earlier ones and circular reasoning is avoided. This height and shadow problem is not just a made-up classroom example. Measuring heights indirectly using shadows is one of the oldest and most natural motivations for similar triangles. According to legend, Thales, who lived in the 6th century BCE, measured the height of the Great Pyramid of Giza using shadows. He waited until his own shadow was equal to his height. At that moment, any vertical object on level ground would cast a shadow equal to its height. So the pyramid's height could be found by measuring its shadow. So essentially he was relying on a special case of the proportionality result, where the smaller object's shadow is equal to its height. In that case, the bigger object's shadow is also equal to its height. Our height and shadow problem gave us right-angled similar triangles. But similar triangles do not have to be right triangles. They can be any triangles. The defining feature is that corresponding angles are equal. From this, one can prove that corresponding sides are proportional. We will explore the general case in the next video. Thanks for watching this one.